let's begin our discussion of Bernoulli trials, which lead in or feed into the binomial distribution. So for our learning objectives, we're going to define a Bernoulli trial. And calculate its mean and standard deviation. We're going to define the binomial distribution. To calculate the probability of a series of Bernoulli trials and then we'll use the binomial distribution to calculate the probability of a series of binary outcomes over many trials. All right. Okay, so first we'll introduce Bernoulli trials and the distribution. Very simple distribution. From the videos, what is a Bernoulli trial? Yeah, so Bernoulli random variable is the outcome of a Bernoulli trial. Yeah, yeah. So we have a binary outcome. Well, I guess we'll kind of get there a little bit later, but just a binary outcome, right? We'll just kind of isolate it as one trial. And the outcome we could say as, so binary outcome, two possible outcomes. And we kind of define the two outcomes as either success, so X is our Bernoulli random variable, and it could equal success or failure. And of course, the binary outcome doesn't have to be a success or a failure. It could just be something happening versus something not happening. That's just a way to think about it. And we'll say success is 1, takes on the value of 1, and a failure is 0. And what were some of the examples from the video of binary outcomes? Or just shooting a free throw, getting a disease, right? You either have the disease or you don't have the disease, you make the shot. Penalty kick, I was coming to that example because we had Val. Do you guys know Val? She was on varsity basketball. She graduated last spring. Yeah, she was French student. So I use a lot of basketball examples. Now we got a soccer player, so she make the penalty kick out. Okay. So that is our random variable. It's kind of very, very simplistic. And we can then kind of further define this and say, let P equal probability of success. And P can take on any value between 0 and 1, right? So it's not just 50-50 each time. A binary outcome is yes or no, but we could have, and we'll also say that is constant over time. What's the probability of making a penalty kick for the average soccer player? 1 in 5, 1 in 2.
If someone doesn't make a penalty kick, I'm like,
what the heck?
Yeah.
Okay, so 90%? Okay, great. I don't know. Just the goalie. Yeah. Okay, so we'll say X is equal making a penalty kick in soccer, just the goalie. And we'll say P is equal to 0.9. So pretty high probability of making a penalty kick. That's awesome. Okay, so is X a continuous variable or a discrete variable? Yeah. But really X is just 0, 1. It just has 2 values. Yeah, so it's a discrete variable. And we'll draw the PMF, the probability mass function of X. We have 0 and we have 1, and this is P of X. And in this case, we said that the probability of 0 is tiny, 0.1. And the probability of success is all the way up here at 0.9. There we go. So this is our PMF, very simple, right? And then we can kind of make this a little more theoretical. And we'll say that this is P up here, right? P is equal to 0.9, and then this is 1 minus P. A little more general. So our PMF, P of X, is equal to this kind of piecewise function, 1 minus P for X equals 0, and P for X equals 1. So what is the expected value of X? What's the mean value? If we do a bunch of Bernoulli trials, what do we expect? Yeah. We could do the formula. Do you remember how to do the mean of a discrete variable? What is the mean? We define the mean kind of probabilistically as the weighted average, right? So it's X times what? Yeah, so it's X times the probability of X. So sum of X times P of X. And then in this case, this is pretty simple, right? We have X is equal to 0 times the probability of 0 plus X is equal to 1 times the probability of 1 of the success. So do this math real quick, and what do we get? Just get P. And then I won't do the variance, but the variance of X, and the way we would do this is just similarly, except it's X minus mu times P of X squared times Px of X. And then we know that mu is equal to P, so I plug P in there. And you can do that algebra, and what you end up with is the variance of X is P times 1 minus P. Okay, so a simple kind of setup here, right? But then we can also do some more statistical analysis of that. So that's our Bernoulli trial. It's just one trial. It's got a distribution. You could take 100 penalty kicks, and if that player or that team's average success rate is 0.9, then you would get this distribution. You could calculate that. You do the mean, the variance, etc. The Bernoulli trial and the Bernoulli distribution are not that interesting in and of themselves. It's when we start to think about successive trials over time. And okay, if we have 5 penalty kicks in a game, what's the probability of 2 shots that we make? What's the probability that we make 3 shots, of 5 shots, etc.? So when you start adding, or yeah, not adding necessarily, but when you start having successions of Bernoulli trials, that's where things get interesting. Okay, so let's do that next thing. And we're going to get to the binomial distribution. Take repeated independence. That's where the independence comes in. Between each trial, the outcomes are independent. So now we've got a new random variable, and we'll say x is now the number of successes over n trials. So it's kind of, there's 2 variables in here now. So it's not just the number of successes, it's how many trials. But we'll note that the order of successes is not prescribed. The order is important because you could have, say you're interested in what's the probability that out of 10 penalty kicks, we make 3. You could do that in many different ways, right? You can make the first 3, you can make the last 3, you can make the first one and then miss 2, etc., right? So there's a lot of ways you could do that. And that's important when you're calculating the probability, but we're not prescribing in X, we're not saying you have to make the first 3. That would be a different can of worms. All right, let's go over to our, see if I can find it here. There we go. Let's go to our tree diagram. And we'll do a, let's see here. We'll just do a coin toss. We'll keep it simple. So we'll say, let X equal the number of heads over 3 coin tosses. Yeah. You know, I am vaguely familiar with what that is, but maybe you can tell me a little bit more about it after class.
1, 2, 2, 1.
Okay. Yeah, this is going to be kind of symmetrical here, so it sounds very similar. All right, so X is the number of heads over 3 coin tosses, and what we're going to do is use this tree diagram to track the cumulative probability. Now we said that each trial is independent, right? If you flip a coin, each trial is independent. So as we accumulate probabilities, what can we do with these to calculate the probability at the end of the outcomes of 3 coin tosses? We just multiply them. So they're independent, so we can multiply them. Okay. And we'll do those 3 trials. So I set up the first one. So success, the probability of success is 0.5. And we can say, okay, trial 1, we get P, 0.5. Trial 2, we get P, 0.5. Trial 3, we get P, 0.5. So this is going to equal to 0.5 to the third. And then I want you all to fill out the rest. So what this looks like is, so we have success, success, and then we have fail. And this is going to be 1 minus P. So P squared times 1 minus P. And I want you to write these out because this will kind of show you how everything plays out. And then we'll go fail here. I'm just going to start writing 1 minus P. Yeah. So we're doing, so we're saying success is up, failure is down. So we did 1 success, 2 successes, 1 fail. And we're just kind of tracking the different potential outcomes. So here's fail is down. So we could have fail, we could have success, success, fail, fail. Does that make sense? Well, I guess trying to figure out.
I was just confused
Yeah.
because on trial 1, like failure went down
Yeah.
a lot. And so I was confused because the fails up top were going down.
Oh, it's just yeah, exactly. It's just how to fit it in. Yeah. So the relative position doesn't matter. I'm just trying to differentiate between successes and failures. And then we'll just track all the way through all the way through. So this is going to be P squared 1 minus P. This is going to be P 1 minus P squared. So we get some kind of symmetry here. It starts with P cubed, it ends with 1 minus P cubed. And then we can prove ourselves that this all adds up to 1. If we want to do that, we can just go here and just say we start with P cubed, and then we'll just combine all the like terms. P squared 1 minus P, P squared 1 minus P. So we get 3 of those. And then P times 1 minus P squared, we have 1, 2, 3. And then we finally have 3, or so we just have 1 minus P cubed. So if you want to prove it to yourselves, you can plug in 0.5 and calculate. And what should this all equal? Should equal 1. Yeah, we have to tell me about that. I'm not familiar with Pascal's triangle. All right, I'll let you guys do the math, but that all equals 1. And so as you go out, you're squaring 1 minus P's and cubing, or, it keeps increasing. And you can see there's a pattern to this. So that pattern can actually be generalized, and we'll do that. So what we're doing here, and I should have done this a little bit earlier, is that we're saying, so we have trial 1, we have trial 2, we have trial 3. And we're saying that we have a success. So this is probability that X is equal to 1, probability that X is equal to 1, probability that X is equal to 1. So success, success, success. And so this is the probability that, this is from Bernoulli. And so if we go binomial, we're saying that the probability that X is equal to 1 for n equal to 3 trials. Or I guess we should say, sorry, this is the number of trials. So X is equal to 3 over 3 trials, right? And then that's just going to be equal to these individual Bernoulli trials, which is just P and P and P, which we can just multiply them together because they're independent. Okay, so let's generalize this into an actual formula. For n Bernoulli trials, where we have that binary outcome with a probability of success P within 1 trial. We're going to say, we'll say Y is equal to the number of successes over n trials. And we'll define first the PMF, the probability mass function. So probability of Y successes is equal to this thing. You've probably seen this before. It's n choose Y. On your calculator, it's NCR. And what that we'll kind of extrapolate that in a little bit. So this is just it's just a constant that you get based on n and y. And then it's p to the y, 1 minus p to the n minus y. And this makes sense, right? We have y successes and then n minus y failures. So that's all we're doing here. And then we have to multiply it by this factor, which gets at all those kind of intermediate outcomes that we looked at. So n, maybe it's NPR. Let's see, bring out your calculators and go to the probability key. Ah, yeah, so it's not NCR, it's N. Oh, never mind. Yeah, it's NCR, okay. Okay. Yeah, so NPR is permutations. And you're gonna get it'll be a bigger number because order matters in this case. Here, this is choose, and C just means choose, and it just means they kind of lump all possible outcomes together. So we know that we can make the first, if we'll go back to the heads example, we can make the first 2 heads and the second one's tails. We know that we could have a bunch of different orders of that outcome, but we don't care about the order. And so we just say over 3 trials, how many heads do we have? So we kind of lump all those together. And that, let's see, do we have the formula for it? Yeah, okay. The formula for this, it's kind of a pain, to type out in your calculator. That's why you get a function. So it's n radical, y radical, n minus y radical. And this is going to be our PMF function. So big P of y. Now the CDF is very similar. We're just kind of summing up to a point. And so I'll write that out, and then we'll play around with our probability key. So this is the CDF is going to be the probability of, let's see here. Big Y is less than or equal to Y successes. And we write that as big F of Y, Y. And so because it's a discrete function, we can't do an integral. So we're just going to sum up over K trials. And I guess we could probably write this as K successes right here. So that'll we're basically plugging in K for Y. So say, what's the probability that we'll have 2 heads over 3 coin tosses? So N is the number of trials, that'd be 3, K would be 2. All right, and then we just write in our PDF, and we're just swapping in K for Y. So let's use our probability NCR key on our calculator and do some probability calculations. We'll start simple. Our function. And let's find out the number of ways we can have number of ways flip 3 heads in 3 coin tosses. So N is equal to 3, and then what is Y? 3 coin tosses. How many successes? 3, right? This is a simple one, but we'll start simple. So we're going to do 3 NCR 3. And what do you think that would be? There's only one way to do it. You have to do it out of all the different potential outcomes. There's only one way to do it, right? So let's say how many times can you do N equals 1 and we have only 1 heads. So this would be 3 NCR 1. And that equals 3, right? We could do the first heads and then 2 tails, the second heads, 2 tails, 2 tails, and then the third one's heads. So 3 ways to do that. Let's do a little more complicated ones. How many 5-card hands can we draw from a deck of 52? What's our n in this case, and what's our y? Yeah, so we have 52 potential outcomes, and then we don't care about the order. We're choosing 5. So let's see how that works out. That is 2.5 million, 2.6 million. What's another example we could do? Say you're going to the slot machine and you want to get at least 2 sevens or 2 cherries. And I don't know how many different options are out there, but let's just say anyone play the slots. We want to get the number of ways to get 2 cherries. You get a little bit of a prize, I think, if you get 2 cherries. I don't know. We're not going for all the way across jackpot. And we have 3 trials. Trying to think if there's another kind of way this would happen, but yeah, well, so we'll do 3 trials, NCR 2. So that's not, I guess that's not too interesting. So we end up with 3 ways to do that, right? That's similar to the heads. Okay. In the homework for this, you'll play around a little bit more. Let's talk about the mean and variance of this distribution. So the expected value of y and as before, it's a discrete distribution. So we sum up the potential values that y could have times the probabilities of those. But we know that it's really just a Bernoulli trial, right? And each Bernoulli trial has a probability of success equal to P. And so if we're just saying, well, each outcome has a probability of P, then we have however many trials we have. So we have n trials. Then the expected value of y over n trials is just equal to n times P. So if we have 100 trials, the probability of success is 0.9. Then over 100 trials, the expected value of the number of successes over thousands of repeated experiments would be 100 times 0.9 or 90. And very similarly, the variance of y is related to the variance of the Bernoulli trial. And now we're just going to do n times P1 minus P. All right, we got about 10 minutes left. Let's do an example. I'll type it out. Okay, and this is, so now that we're kind of learning multiple distributions, we can use multiple distributions in a problem together. So we'll start off with a normal distribution, and then we'll apply it in a binomial distribution fashion. So the annual rainfall in Orange County, California, follows a normal distribution with mu, or just say mean, is equal to 15 inches, and standard deviation is equal to 4. So we can write that out as x follows normal, 15, 4. Mean, standard deviation. All right, so the water distribution company has a policy about drought that a water shortage. So we've got a water shortage. Everyone needs to start conserving water. A water shortage is declared in May if only 7 inches has fallen in the preceding 12 months. All right, we look back at the last year. How much rain have we had? It's May. We kind of know the overall climatic cycle. We could do this. We could apply this to Grand Junction very easily. We could say, okay, what's our snowpack in, say, March or April, before people really start irrigating? We know how much water we have up on the mountains because we can measure that. And if you go on the field trip, Jaden, you're totally invited. March 12th, Grand Mesa snow survey field trip, water supply field trip, over here in the Green Valley. Can ski at Powderhorn too. You know, we'll learn how they go out and actually measure the water supply in the snow. They dig a big pit, they take a core, you can weigh the mass of that snow, you know, the volume, so you can calculate the density. And then that gives you a point estimate of the liquid volume of water in that snowpack. And the city of Grand Junction actually goes around to all their reservoirs and does that every month to get an estimate of how much water, kind of point by point across their watershed. So this would be a common thing, right? And in Orange County, it's a Mediterranean climate, so most of the precipitation falls over the winter, I think, and then it dries up in the spring, something like that. Okay, so here's the policy. We kind of look back retrospectively. Do we have 7 inches or not? All right, so here's the question. What is the probability that at least one shortage will occur or be declared, right, in the next 5 years? So there's 2 parts to this question. The first part is we want to calculate the probability that we have a shortage in a given year. What's that probability? How would we write that out? Take a second to think about that. So X is our annual rainfall. This is the probability that X is less than 7 inches. I guess it's less than or equal to. says only 7 inches has fallen, so less than or equal to 7. So first we need to calculate that probability, and we're going to use that based on the normal distribution. And then the second part is we need to use the binomial distribution to calculate probability that, and now y is the number of shortages over n years, right? So y is equal to 1, or n is equal to, given that n is equal to 5. All right, so not too bad. It's just 2 calculations. We've got 2 minutes. I think we can do this. All right, we'll kind of move quickly. We'll say, how do we calculate the probability that x is less than or equal to 7 using the normal distribution? What's the kind of function that we plug that into? Yeah, so we can use the standard normal variate in the phi function. So phi z, where x is equal to 7. So we do phi, we say x is equal to 7 minus the mean, which was 15, all over the standard deviation, which was 4. So this gives us phi of -2. And we want less than or equal to, right? So is this calculating what we want to calculate? The probability up to this point? Yeah, that does. So we can plug that in, and then we get 0.0228. So what does this represent, this probability here? In 1 year. So this is P for our Bernoulli, right? And binomial. The probability of success or failure. We're saying a water shortage is a success in this case, right? Because we want to calculate the probability of water shortage. So this is our P value. Now we go to the next part of this. And so we want to say, what's the probability that y is, we said at least 1. So how do we write that out? How do we write at least 1 water shortage? Greater than or equal to 1. So it could be 1, it could be 2, it could be 3. Okay. So greater than or equal to, but we know that the CDF doesn't give us greater than or equal to. How can we write this in terms of a CDF function? Or even a PDF? Okay, so y is less than 1. And we could do the CDF, but we know that the PDF is a little easier to use. And so if y is less than 1, this is just 1 minus the probability that y is equal to 0, right? If it's less than 1, it has to be 0 because it's a discrete variable. Okay, so now this is what we want to calculate using the binomial PDF, 1 minus the probability that y is equal to 0. So I'm going to do that real quick, and then we'll round it off. Okay, so this gives us 1 minus, and then we'll do that PDF. So n is 5 years. How many successes? We're going to say 0 successes, because this is what we're calculating. And then we do the actual PDF. And maybe I'll write it out over here real quick. This is 1 minus n choose y, p to the y, 1 minus p to the n minus y. So plug the numbers in over here. Our probability is 0.0228. We raise that to y is 0. And then we get 1 minus 0.0228 to the 5 minus 0. Plug those numbers in, and we get about 0.11, or an 11% chance of at least one water shortage over 5 years. It could be more, right? And then I will show you how to do this in R very quickly. This would be 1 minus d bin, so d for density, or the PDF function, bin for binomial. And then the arguments for that are y, n, and p. Those are the 3 variables that you need to plug in. So you'd say 1 minus d bin, 0, 5, and 0.0228. And then that'll do the calculation for you.